We are not able to hear you. Hello, Mr. Deepak? We can't hear you.
Is it same now? Because I
Uh,
am
yeah, now we can hear you.
so sorry for this technical glitch. Let me share my screen and we will start from there. My screen is visible, correct?
Yeah, it's visible.
Thank you. Thank you everyone for your patience because of this technical glitch. My name is Deepak Singh and I'm a principal solution architect with over 20 years of experience in enterprise software engineering, cloud architecture, and digital transformation. My work focuses on designing scalable distributed system, cloud native architectures, enterprise security, AI-driven solution. And today I'm pleased to share my work on AI-driven adaptive and secure orchestration for distributed enterprise system. As enterprise technology environment become increasingly distributed across cloud platform, on-premises infrastructure, edge environment, and microservices, orchestration become much more complicated. Traditional orchestration platforms are generally very effective at executing predefined rules, but challenge is what happens when the environment changes faster than those rules can adapt. What happens when workload suddenly increase, network contingent change, or one of the participant node became showing abnormal or potentially malicious behavior. The framework I'm presenting today explores how AI-driven interface, adaptive orchestration, security enforcement, synchronized execution, and continuous feedback can operate together as a one control system. Let me first give an overview of what we are going to cover today. This slide is divided into 5 parts. The first, I briefly explain the problem context and why conventional orchestration become difficult in highly distributed environment. Second, the core technical contribution of the proposed framework. Third, we will look at overall architecture and method flow. Then I will spend some time on 2 areas that I believe are separately important. First, integrated security and adaptive behavior. And finally, I will summarize the main technical takeaway and some potential area where this type of orchestration model could be applied. So rather than looking the AI as an isolated capabilities, the discussion today is really about how AI can become part of enterprise control law. Before going deeper into the architecture, let me briefly establish the patent context. This patent we filed in April 21, 2026 with US Utility Application number 19654-288. The title is System and Method for AI-Driven Adaptive and Secure Orchestration Framework for Distributive Enterprise Systems. Most conventional orchestration systems rely heavily on predefined rules, the threshold, and policies. These mechanisms work well when system behavior is reasonably predictable. But distributed environments are increasingly dynamic. Workload may change within the second, node become unavailable, latency may suddenly increase, and resources demand may shift between locations. The second challenge is that security orchestration and often treated separately. The orchestration platform may define whether something should run, while another security platform define whether that execution is safe. The separation can create delay between operational decisions and the security response. The third challenge is the distributed state management. Cloud edge, on-premises, infrastructure, and microservices may all produce telemetry at the slightly different time and from different environments. So the fundamental question became, can orchestration become adaptive, security aware, and continuously informed by the actual state of the distribution environment? That state problem the framework attempt to address. The core technical contribution is closed loop AI assisted orchestration framework. The important frame here is a closed loop. This system work, observe, analyze, decide, secure, execute, and learn. Telemetry from distributed system provide observation layer. The AI-assisted inference analyzes the that telemetry to identify the workload changes, saturation condition, anomalies, and other relevant patterns. The resulting insight is then converted into the orchestration decision. But, and this is the important, the decision is not immediately executed. It must first pass through the security layer and the policy layer. Only after validation does the framework coordinate execution across distributed environment. Then the outcome of that action generate new telemetry. That telemetry become input for the next decision cycle. So the novelty is not simply adding the AI to an orchestrator. It brings telemetry, AI inferences, adaptive decision making, security enforcement, synchronization, and feedback together within the same operational closed loop. Let's look what is the closed loop. If you see in this diagram, on the left side, we have a distributed input environments. That telemetry flow into the AI-driven orchestration controller, which is the central logical component of the framework. The controller evaluates and the incoming information determine whether the changes are required, checks the associated security condition, generate appropriate orchestration action. Those actions might affect resources allocation, workload placements, routing, communication path, or security containment. The action are then executed across the managed distributed environment. But notice that the most important part of the diagram, the process does not stop after execution. The resulting system state generate new telemetry which come back into the controller. That create the closed loop. The architecture therefore move from monitor and execute toward observe, reason, execute, measure, and adapt. Now let's open the controller and look at what happened inside of it. The first is the telemetry execution. This collects the system, workload, infrastructure, and security signal from participating nodes. Second, the feature extraction. Raw telemetry by itself may not be meaningful to the inference model, so it is converted into indicators such as utilization pattern, variance, workload trends, dependency behaviors, or anomaly check characteristics. The third function is a predictive inference. This is where AI-assisted analysis help identifying abnormal behavior or predictive upcoming resources or workload condition. The fourth function is a policy decision. Inference alone does not control infrastructure. The result must be translated into an orchestration action. Then we have a security enforcement, which validate whether the proposed action is authorized and acceptable from prospective risk. Then we have a synchronization, coordinate execution across distributive nodes. And finally, audit logging, capture the decision, reasoning, context, and resulting action. So collectively, these seven functions create, observe, predict, secure, act, and learn. The method flow, adaptive and secure orchestration show this process began by collecting telemetry. The telemetry is then normalized and buffered so from the coming different system can be processed consistently. Relevant feature are extracted, passed to the inference layer. The system then, whether there is an important workload change, abnormality change, security concern, and when no significant change is detected, monitoring simply continues when a change defined, however, the framework generate or adaptive orchestration decision. Before the decision passes through security policy validation, this critical design principle, AI recommendation does not automatically equal execution authority. Security and policy remain part of the control path. And therefore, when the system identifies a potential compromise component, it can initiate state contain rather than immediately performing shutdown after the execution is executed and resulting state feedback into the monitoring process. This becomes easier to understand when we view it as a continuous operational pipeline. This flowchart shows how an orchestration cycle moves through the framework. The process begins by collecting the telemetry. The telemetry is then normalized and buffered so information coming from different systems can be processed consistently. The relevant features are extracted and passed to the inference layer. The system then determines whether there is an important workload change, anomaly situation, condition, security concern. When no significant change is detected, monitoring simply continues. When a change is identified, however, the framework generates an adapted orchestration decision before execution that passes through the security policy validation. This is a critical principle. AI recommendation does not automatically equal execution authority. Security and policy remain part of control path. And when the system identifies potentially compromised component, it can initiate stage containment rather than immediately performing a complete shutdown. After the action is executed, the resulting state feedback into the monitoring process. This becomes easier to understand when we view it as a continuous operation pipeline. It has a acquire, extract, inform, control feedback. First, we acquire the real-time statistics. Second, we extract the meaningful indicator. That could be include variance, dependencies, pattern, utilization trend, or other characteristic of a distributed environment. Third, AI inference evaluated those indicators. For example, the model might identify as emerging saturation condition or abnormal node behavior. Fourth become the control action. Then these all combine together and describe there is a what is need important aspect of the architecture is how inference can operate across both logical and global conditions. The two-stage neural inference, the process model used two stages. The first stage operates closer to the individual node or local environment. Here the system analyzes node-specific telemetry. It can evaluate local workload condition, resource pressures, anomalies, health indicator. The advantage is a low latency. A local environment does not necessarily need to wait for single signal across the entire enterprise before identifying that something unusual is happening. The second stage perform global aggregation. Indicate generated by multiple nodes are combined to understand broader system condition. This is important because a situation that appear abnormal from the perspective of one node may become significant when correlated with activity across many nodes. The global stage can support coordinated decision involving workload placement, routing capacity, distribution, or containments. So conceptually, local intelligence identify condition quickly, while global intelligence coordinate the enterprise response. Adaptive telemetry mechanism extremely important in a distributed environment. There are two concepts highlighted here. First is a closed loop adaptive sampling. We do not necessarily need to collect every metric at the same frequency all time. When system is stable, very high frequency sampling may create unnecessary processing and network overhead. But when the framework is detect high variance or abnormal behavior, it can increase the sampling density. In the other words, the system pay more attention when conditions become unstable. The second concept is temporal synchronization. Distributed nodes do not always report event at exactly the same time. Network latency, geographic distance can create timing differences. If those events are interrupted without considering the timing alignment, the controller may create an incorrect picture of the system state. So the framework aligns the telemetry into common temporal context before using it for the distributed decision making. The principle is simple. Better decisions require better context, and better context require both accurate and time-aligned telemetry. Once the execution takes place, the framework can also use outcome to improve the control behavior. Observe, act, learn. The system observes real world behavior. It takes an orchestration action, then evaluate the result. For example, suppose workload is moved from one node to another, become the system predicts situation. The framework can evaluate whether the move actually reduced latency, improved utilization, or stabilized the environment. The outcome become part of next policy evaluation. The objective is not uncontrolled self-modification. Enterprise systems still require security boundaries, governance, and policy constraints. The objective is to make the orchestration layer progressively more responsive to observed system behavior. And another important considering is avoiding overreaction. Our system should not continuously move workload simply because metrics changes slightly. The policy layer therefore need a significant boundaries to avoid unstable or excessive tuning. So this become an adaptive control system rather than static routing mechanism. The entire concept can be remembered through five verbs: observe, predict, secure, coordinate, learn. First, observe. The system gathers telemetry from cloud, edge, on-premises infrastructure, and distributed services. Second, predict. AI-assisted inferences evaluate both current and historic signals. Third, secure. Every orchestration action remains subjective to policy, validation, authentication, authorization securely controlled, and when necessary, stage containment. Fourth, coordinate. Action are synchronized across the distributed environment rather than being performed as independent changes. And the fifth, learn. The result of those actions feed next orchestration cycle. So, if I had to summarize the technical contribution in one sentence, the framework transformed distributed telemetry into secure, adaptive, and synchronous orchestration action through a continuous evolving control loop. This is the first modern distributed orchestration required context. The second takeaway is AI become much more useful when connected to the control execution. Prediction by itself does not operate infrastructure. The real engineering value come from connecting inferences with the orchestration decision. security, validation, synchronization, and measurable outcomes. And the third, security response, does not always have to be binary. Stage containment provide an alternative where the system can progressively throttle, restrict, or isolate a component based on changing risks. Ultimately, the contribution I wanted to share today is the integration of this capability into one adaptive framework. Telemetry, inferences, policy control, security, synchronization, and continuous optimization. And this concludes my presentation, and I'm happy to take any questions from here.
So, as there are no questions at this moment, thank you, Mr. Deepak, for your insightful presentation on AI-driven secure orchestration. We sincerely appreciate your time, knowledge, and valuable contribution to ICAITS 26. Thank you so much.
Thank you.